Human balance is the ability to keep the body stable and prevent falling when standing or moving. It is essential for our health and quality of life due to its necessity in sports, exercise, and all kinds of daily life activities. Prevent falling is a challenge for human balance control given that we are bipeds. The bipedal standing or walking is inherently unstable to maintain balance. The balance control system may become a non-trivial risk of falling with degeneration caused by aging or pathologies. According to the data from CDC, falls are the top public health problem for older Americans. Over 25% Americans older than 65 experience at least one fall each year. When the first fall happens with or without the injury, they could have fear of falling and less movement, and this could bring them the second fall and even more injuries. Once a vicious cycle begins, it could be hard to break. Tripping over an obstacle and multitasking are the two top causes of falls, and they are particularly challenging for aging adults. Aging adults often fall when stepping onto a curb or over an obstacle, either because they did not notice or could not clear it safely. They may also have difficulty walking safely when engaging in multitasking, such as memorizing numbers. Balance is achieved by multiple systems working together, such as sensory inputs and cortical control. Visual, somatosensory, and vestibular are known important sensory inputs for balance. Cognitive load plays a significant role in cortical control. Recent research suggests that auditory cues are important for balance as well, and that people with hearing loss are at an increased risk of falls. Our team is working towards better understanding of the relationship between balance and the stimuli of visual, auditory, and cognitive load. Given all the problems aforementioned, we believe it could be groundbreaking to implement a VR system to assess balance in the walking paradigm with obstacle negotiation under different conditions of visual cues, auditory cues, and cognitive load. Some existing VR systems for virtual rehabilitation have shown a number of advantages compared to conventional method, but there is a long way to go due to some gaps such as clinical acceptance, high expense, and the requirements on technical effort. And also we need sensitive systems to identify the underlying causes for imbalance before specific training or fall prevention programs. In most of the cases, clinicians and the researchers need to evaluate subjects with controllable and repeatable trials so that they can individualize the training to the subject's needs. The lack of a sensitive assessment system makes us think about how to design a system to investigate walking balance and obstacle negotiation under sensory and cognitive load. What metrics that clinicians and researchers would find useful can be measured with the system, and how to make the system more accessible to clinics or researchers.
Let me show an overview of the system, and then I'll talk about each component in detail. In the system, we use HTC Vive iPro to track gaze and present VR environments with spatial audio. The wireless adapter makes it untethered, Vive trackers mounted on the ankles to track obstacle negotiation, and the pressure sensing walkway to get pressure variances.
With the VR platform, our system provides three major stimuli. Each of them needs to have low and high intensity. The first one is a visual stimuli. In the VR environment, objects have movement to create a visual flow in the high intensity test, but in the low intensity test, everything is stationary. The scene contains city-like urban blocks with cars moving around, randomly generated buildings, virtual avatars on the street walking from one side of sidewalk to the other side, virtual obstacles generated on the sidewalk with controllable heights. Garbage bins are the boundary of the walking path. Participants can cross virtual obstacles while walking along the sidewalk back and forth during a 60-second trial. Our focus was not on the fidelity of the graphic models, because what we want to have is visual flow. It is generated by the movement of the graphic models. Previous studies have shown that high-fidelity visuals do not necessarily have better transfer to everyday function than abstract and simple visuals. But abstract and simple visuals are less expensive on computation, so we could have smoother rendering. Participants are less likely to experience cyber sickness. We aim to enhance the immersion and presence in the scene by adding 3D realistic sounds. So the second one is auditory stimuli. There will be a bustling streets in the high intensity test and no audio in the low intensity test. The implementation of sound in the system is based on spatial audio in order to increase immersion. It allows for a rich soundscape in all of the directions around the listener. There are two main audio assets, object sounds and ambience. Object sounds are attached to objects, including the sound of footsteps, cars. Ambience is created from the original recording in New York City, including city rumbling sound and crowd chatter. For the cognitive stimuli, there are motor-only tasks for low level, including walking and obstacle negotiation. In the high level, we use multitasking, such as memorizing numbers, to overload the working memory, which is closely linked to cognitive load. Maintaining a stable gait under multitasking becomes more challenging for aging adults. Cognitive interference in walking was found to reduce gait speed and increase gait variability in older adults and individuals with neurological defects. Moreover, a correlation between increased risk of falls and changes in attention domains designated to walking was found in older adults walking while talking. Our system can provide cognitive tasks with motor tasks, where participants are asked to walk and cross the obstacles while listening to a list of narration-like decorative sentences, such as "meet me at 4, 2 apple trees." 7 random sentences will be played in each of the 60-second trial. Subjects need to remember the numbers at the end of each trial. We are going to have subjects walking or crossing obstacles with a combination of each level of this stimuli. We wanted to test them with all these levels and find where their weaker link is. And also it is important for us to know how they react to specific conditions.
Gaze tracking is the most recent integration into the system. It helps us to analyze the subject's eye movement during the motor tasks. It can give us a chance to understand how the eye movements respond to motion of the head and the obstacle negotiation when we walk and turn. The right highlight was just for experimenters to understand the real-time gaze focus. The feedback does not have to be provided for subjects.
Obstacle negotiation is another focus of our system. The system has the ability to test people's response to anticipated or unanticipated obstacles. In the anticipated obstacle experiments, all the obstacles are generated with a height selected at the start of the scene. Participants can have enough time to plan the obstacle negotiation strategy. In the unanticipated obstacle experiments, all the obstacles are generated with a selected height, but at a random time. Participants will not be able to predict how far or when an obstacle will appear in front of them. They have limited time to respond to the suddenly appeared obstacle by immediately adapting to a new strategy and executing the new strategy to avoid tripping over and maintaining a balanced gait pattern. We measure available response time, which is R, in the experiment to quantify the walking balance ability in obstacle negotiation. R is the time to respond to the presence of the obstacles. It is correlated with the participant's walking speed and distance of presence in front of the participants. People with better walking balance ability usually have less R. A pressure sensing walkway senses foot pressure and visualizes it in a heat map. This helps to assess walking balance via pressure dynamics per foot. The pressure sensing technology used in the study is a pressure mat by Tectonic Technologies, which consists of a matrix of 4 sensors, where the sensory nodes are distributed at half-inch intervals. Each node can sense pressure from 50 gram up to 5 kilogram. Each sensor system is 24 by 16 inches. Pressure mat is sensitive to pressure variances. The pressure mat is affordable and portable, so that it is much more likely to be widely used in clinics or at home. Multiple pressure sensors can be tied together to create a larger pressure sensing surface. This allows us to develop a pressure sensing walkway to gather dynamic pressure of gates. We have tested the walkway length from 5 meters up to 15 meters due to the space requirements for a reasonable range of walking and the tracking capacity of the VR system.
The setup of the whole system includes one set of HTC Vive Pro I VR system with a wireless adapter, 2 Vive trackers, and 6 tectonic floor mats. The floor mats can be placed in a 2x3 layout or in a single line. The cost of each pressure sensing mat is around $500, and the total cost of the setup is around $5,000. The number of the floor mats can be increased or decreased depending on the requirements for the walkway length. With all the components working together, here comes the system. The merit of this project is to present an affordable and ease-of-use assessment system, which can collect foot pressure dynamics, gaze tracking, and kinematics of head and ankles, so that clinicians and researchers could use it to assess subjects' walking balance and obstacle negotiation under various sensory input and cognitive load. This specific assessment can then guide fall prevention programs individualized to the participants' needs. The low cost and ease of use will potentially increase the clinical acceptance and outreach to communities so that it can be widely available for assessment and treatment of participants with balance problems and fall risk. With the system, we can get interesting metrics. For example, success rate of obstacle clearing, available response time for unanticipated obstacles, head parameters such as accelerations, gaze tracking such as ratio of gaze fixation on obstacles, and the spatial and temporal gait parameters such as length and time of step and stride.
This project is the outcome of our collaborations across NYU Courant, Steinhardt, Tandem, and Tectonic Technologies. We are funded by NYU Aging Incubator